Hello everyone and welcome to the course Laplace Transform. This is the second session of this course. In the previous session, we learned a little about the Laplace and we also learned the formulation and definition. And in this session, we are going to learn new points and also solve the first example. Let's start from here. Let's assume that we have a function that I'm going to call it f, and this is a function of time, so ft, which is available for t greater than 0. And I'm going to calculate the Laplace of this function. I usually use this symbol to show the Laplace. So the Laplace of ft is something that I'm going to calculate. So let's use the definition for this means. So the Laplace of ft, this one, equals the integral from 0 to plus infinity exponential minus st, and then the function. This is the kernel, and then the function gonna be ft dt. And the answer of this integral gonna be a function of s, so I can show it by a small of s. And that the s is the new variable. That is like at the beginning, the function was a function of time. The variable was t, time. But here we change the variable. We change it to s. S is the new variable, which is, of course, belong to r. But the point is that this integral here is a special type of integral. We usually call it improper integral. That is like there are some values of s that there's no answer for this integral. That means this integral doesn't converge for some values of s. So in those cases, the Laplace of ft cannot be calculated, right? So this is a really important point for us. We need to know for which values of s the Laplace of f is available, and for which value of s the Laplace of f is not available. This is a really important point to consider. I'm going to explain about it to describe this point further by an example. So I'm happy to start the first example of this course, example 1. Our example is the Laplace of the function ft. The ft is just equal 1. That is like my function is this one here. That if this axis is t and this axis represents f, so my function is something like this. That is, for any value of t, this function shows me only 1. And I'm going to calculate the Laplace of this function. So let's use the definition directly to calculate this Laplace here. So I'm going to calculate the Laplace of the function 1. According to the definition, this is going to be the integral from 0 to plus infinity, the kernel, which is e to the minus st, and then the function is 1, dt. That is like I'm going to calculate the integral from 0 to plus infinity exponential of minus st, right? I'm going to use a really nice trick. Instead of this plus infinity, I'm going to put L. So this would be the integral from 0 to L exponential of minus st dt. And then I'll put a limit here that L approaches infinity. So these two are going to be equivalent, right? And this integral here is not difficult to calculate. I can simply calculate this integral. Let me first put the limit here when L approaches infinity. So the answer of this integral gonna be minus e to the minus st over s. But from t equals 0 to L. So let us to calculate it first for L. I put the limit here. L approaches plus infinity. So if I put L here, gonna be minus exponential of minus SL over S. And if I put 0 here, the numerator gonna be exponential of 0, which is 1. So it's gonna be minus 1 over s. So we have plus 1 over s here. So let me take out the 1 over s. So the answer gonna be 1 over s, the limit when L approaches infinity, minus, sorry for that, exponential minus SL. So I can take out minus 1 over s. So this gonna be exponential of minus SL minus 1. So the limit of exponential minus SL when L approaches infinity, this one gonna be 0. So our answer gonna be 1 over s. This is the Laplace of the function 1. And the nice point here is that this function is available when s is greater than 0. So this one here is what I call it the convergence criterion. The s greater than 0 is the convergence criterion for the Laplace of 1. And we just saw how we can understand for what values of s the Laplace of 1 can be defined. Thank you so much for listening to me. In the next session, we are going to solve more examples.